Okay, we're live, John. So thank you everyone for joining us today. We have the pleasure of John Bywater hosting for us today, the webinar. Thank you so much, John. If you have any questions, please ask them throughout, but we will be answering them at the end. But if you think of some before, you can put them in the chat and then we can answer them for you at the end of the webinar. So please take it away, John.
Thank you very much, Natasha. Welcome, everybody. This is a little session about the Python gRPC client for EventStoreDB. Firstly, we're just going to look quickly at what EventStoreDB is. EventStoreDB is a specialist database for storing events. Each event in EventStoreDB is recorded in one of many streams. A stream is an ordered set of events that all have the same stream name. Each event has exactly one stream name, one stream position, and one commit position. Events are ordered in the stream by their stream positions. Events are ordered in the database by their commit positions. Stream positions, each stream position is occupied by only one event. Each stream position is identified by an integer. The stream position integers of a stream form a zero-based and gapless sequence. And the commit position, each commit position is occupied by only one event. Each commit position is identified by an integer, and the commit position integers in the database form a zero-based sequence, but not a gapless sequence. So the basic picture is there are events in EventStoreDB, and they're organized in many streams. So the big question is why EventStoreDB? For storing events when there's lots of databases. So apart from the great features, one of the great qualities of EventStoreDB is that, to a good approximation, the insert time for an event is order big O1 rather than log n, as it is for databases that use a big tree index, which means that as your volume of recorded events increases, the time it takes to insert another event is pretty constant. And that's not the case for databases that have a B-tree index, as you can see on the graphs, with the EventStoreDB green line being quite flat, and for Postgres it's falling off. The blue line is the total amount of events that are recorded over time. So as time goes by, the Postgres line gets a little bit flatter, and the EventStoreDB line carries on going up straight. So to use EventStoreDB, we're just going to look quickly at getting the server going, because the client needs the server to be running. EventStoreDB is shipped in Docker containers, and there's quite a few different versions of them. The latest LTS versions 21, 22, and 23.10 are available on Docker Hub, and you can use them in your Python project if you want to. Those are the ones that are used in the Python gRPC client project. To start a secure EventStoreDB server for development, you just need to run that Docker command. The code is in the project repository. For the secure server, there's a DB URI that you need, which looks like the green thing there, esdb://admin change it at localhost:2113. The admin change it thing is the default username and password. And for a secure EventStoreDB server, you also need to just pick up a SSL certificate, which you can grab from the server. Obviously, in production, you'd have to get something else. So alternative to the secure server, you can start an insecure server. You can do that with this Docker command instead, and the DB URI is slightly different. You don't need to include the user info part, but you do need to provide the query string TLS equals false. So those are the two connection strings. So alternative to running a single node server, you can run cluster, and there's code in the repository too in another places for starting a cluster of EventStoreDB servers using Docker Compose. So let's get on to the gRPC client itself. The first thing to say is that the client is provided by the Python package ESDB client. The ESDB client package has a stable API now, and it's also supported by EventStore Limited. The test suite has 100% line coverage, for what it's worth, and line and branch coverage, and it's tested with EventStoreDB LTS versions 21.10, 22.10, 23.10, 23.10 being the latest one. It's tested with and without SSL TLS, so both with a secure and an insecure server. And it's tested across Python version 3.7 to 3.12. And the code has typing annotations checked strictly with MyPy, which should help your development against this thing. And it's formatted with black and iSort in case you want to look through the code. It should be pretty standard to look at. And it's checked quite carefully too. We use Poetry for package management during development and for building and publishing distributions to PyPy. You can install a Python client using pip. You just need to run install pip, and you can add the Python the package to your Python project if you happen to use Poetry in your project by just running Poetry add ESDB client. As you can see, the license is a BSD license, and the code is marked as being production stable. The latest version as of today is 1.0.12. So let's get on to the code. The client package, the ESDB client package provides the class EventStoreDB client, and you can import that from the package. As you can see, the client's most useful methods are the following three. Append to stream, because all events are in streams, and if you want to record new events, you have to append an event to a stream. You can read a stream, and the append to stream and read stream methods go together because quite often you'll be wanting to do event sourcing. And to do event sourced aggregates, for example, each aggregate will have a stream, and when you evolve the state of the aggregate, you will generate new events that you will want to append to its stream. And then to reconstruct the current state of the aggregate, you will want to read the stream for the aggregate. And then if you want to propagate the state of the application as a whole, you will want to get all of the events from the database and process them in a downstream component. And the subscribe to all method is a very handy way of doing that. We'll talk about all of these methods and more in more detail shortly. First, I wanted to mention that the package also provides an async IO client, which has the same method signatures as the non-async IO client. But obviously, to use them, you have to use the await syntax. And if you're going to iterate over this catch-up subscription, for example, you need to use the async for in await special syntax for doing that, which I'm sure people who are familiar with this are familiar with. Okay, so moving on. Firstly, the client needs to be constructed. It's a class that you import, and it needs to be constructed. It only has two constructor arguments. The first one is a URI, the connection string URI, and the second one is optional, which it's required if you need to pass a server certificate in or root certificates if you're connecting to a secure cluster or node, but you don't need to if you're connecting to an insecure one. The connection string URI is pretty standard across all clients for EventStore. It's a standardized thing, and there's quite a lot of options for that. So let's just look at the schemes. There's two schemes. They're quite similar, but I'll just describe them quickly. They're defined here roughly in extended Bacchus now form. So the ESDB plus discover URI scheme has the ESDB plus discover : / scheme indication at the front. Then it has an optional user info string, followed by an @ sign, and then a cluster domain name, followed by an optional query string. The ESDB scheme, on the other hand, has the shorter ESDB : / beginning, with the same optional user info, followed by a number, one or many gRPC targets, followed by the same optional query string. The difference is that with the ESDB discover scheme, the client will use the cluster domain name in a query to a DNS server to pick out A records, which it will then use as the gRPC targets, as if you'd put them in with the ESDB scheme. So that's the difference. And once it's got the gRPC targets, the way the client works is that it connects to the one or many of the targets. It tries to connect to the targets to obtain cluster info from the targets. From that, it can identify which nodes in the cluster exist, which are leaders, followers, and so on. And then you can provide a node preference in the query string, and the client will connect to one of the nodes in the cluster according to your client's node preference. So if you prefer to connect to a leader, it will try to find a leader. If you want to connect to a follower, it will try to find a follower. The user info part is quite straightforward. It's just a username and a password. However, the query string has quite a lot of options. There's the TLS option, which we saw before. That can either be true or false. It's true by default, and it's false. It needs to be false if you're connecting to an insecure server. Otherwise, it won't work. So that needs to be matched to the state of the server. If it's an insecure server, it needs to be TLS false. Otherwise, you can leave this option out. Probably the next most interesting thing is the node preference: leader, follower, read-only, replica, or random. The connection name is kind of, you can set that if you want to, but it defaults to a random number. That lets the server know what the client is that's connecting to it for sort of continuity reasons. And then the other things kind of just configure timeouts and discover attempts and so on. All the methods have a timeout value, and you can set the default in this too. Here's a little table of all of the options and their default values and description. This table is on the in the documentation for the client. I won't dwell on this too long. So events in EventStoreDB. An event in EventStoreDB is a recorded fact. EventStoreDB is a store of events, so we need to just think about what an event in EventStoreDB is. It's a recorded fact that has various factors. It has a stream name, it has a stream position, it has a commit position, an event type, data, metadata, and an ID. And as we said before, each event has one stream name. Each event is only in one stream. It has a stream position. It has one stream position which is uniquely occupied by an event, and it has a commit position which orders the events in the database. When we're recording new events, we can use the new event class to construct event objects. This is how that class is defined in the client code. The type and the type and data arguments are required. As you can see, they don't have default values. The metadata, content type, and ID arguments are optional. The content type is application/JSON by default, and alternatively application/octet stream if you just want to put in binary data rather than JSON documents. And the event ID is usually auto-generated when the new event object is constructed. The ID governs the idempotent behavior of inserting events and provides a unique ID for the event. The event objects can be constructed, for example, like this. Let's say we have 3 different types of event: order created, order submitted, order cancelled. We can just create them like this: event 1, event 2, event 3. These events will be will appear in subsequent slides. The data is in the first case is a serialized Python dictionary with a key order number and a value 1, 2, 3, 4, 5, 6. It's just an arbitrary string here, really. There most likely will be other keys and values, and subsequent events will carry their own data too. But for simplicity, it's just been put down like this here. So when reading events from the database, we have we get event objects that are instances of the recorded event class. Recorded event class has more attributes than a new event. In particular, you can see it's got the type, data, metadata, content type, and ID. But in addition, it has the stream name, stream position, the commit position. It also has a retry count and a link attribute, which are used in some cases. The stream name is obviously known by you when you're recording events, but because you tell the database where to record them in which stream. The stream position and the commit position are set by the server when it records the events. The stream position can largely be predicted, but the commit position can't. When you read events that are recorded, then you get those values back. So going back to remembering the synopsis, the first method that we saw was the append to stream method. So sometimes streams exist, sometimes they don't. We can create a new stream by calling the append to stream method. We give a stream name. We have the other required arguments are current version and events. The current version, when a stream does not exist, is this special thing, stream state no stream. That indicates that you know that the stream does something that it does not exist. The events argument is a sequence of new event objects, as we saw in a few slides ago. When we append to a stream, we give a sequence of events, and the operation is atomic, so that either all of the events are recorded or none of them are. The current version argument has to be either a stream state or an integer. There are other values of the stream state of no stream, which we'll look at in a minute. But if you set the current version to either be no stream for when a stream does not exist and you're wanting to create it, or an integer, which is when you already have a stream, then if you get the value wrong, the exception wrong current version will be raised, which provides concurrency control for the recorded events in a stream. So if we want to append an event to a stream when the stream exists, we have to do something very similar, but the current version has to be an integer, and the integer current version should be the stream position of the last recorded event in the database. which you can predict because the stream positions are zero-based and gapless. For example, if a stream has one event, the current version should be 0. If a stream has 2 events, the current version should be 1, and so on. The correct current version for a stream can be obtained by calling the getCurrentVersion method, which returns no stream if the stream does not exist. However, normally you would want to take this version number from your reconstructed aggregate. For example, if you get all the events, reconstruct your aggregate, and the aggregate version is then, let's say, 2, then the current version will be 2, and any new events will be then 3, 4, 5, and so on. So you wouldn't normally use the getCurrentVersion method. It's just a convenience in case you need to have a look what it is. But you'd want to use it from the current state of the aggregate so that you can have concurrency control over the evolution of an aggregate. And you would use the stream positions of recorded events that you use to reconstruct the aggregate to derive the next current version when you're appending new events. So concurrency control, as we've seen, is provided when the current version is either an integer or no stream. However, the currency control can be avoided by using stream state any and stream state exists. So if you use stream state any, then that totally disables the concurrency control. So if the stream does not exist, it will be created. And if it does exist, the event will be appended to it. If you use stream exists, then you'll get the wrong current version error if the stream does not exist. Otherwise, the event will be appended regardless of the fact you're not saying what the correct integer is. One interesting and important quality of the append to stream method is that it's idempotent. It's idempotent with respect to the ID value of new event objects. If the append to stream method is called with events whose ID values are equal to those already recorded in the stream, then the method will return successfully with the commit position of the last new event without making any changes to the database. This is because sometimes it may happen when calling append to stream that new events are recorded successfully, but somehow something bad happens before the method call can return successfully to the caller. In this case, we cannot be sure the new events have in fact been recorded, and so we may wish to retry. If the events were in fact recorded successfully, it is convenient for the retried method call to return successfully without either raising an exception or creating further event records, depending on whether the thing already exists or doesn't. The append to stream method has 2 other optional arguments, which I'll mention here, because they're supported in all the client methods. The optional timeout argument is a Python float that sets a maximum duration in seconds for the completion of the operation. And the optional credentials argument can be used to override call credentials derived from the connection string URI. And before we move on, it's probably, we've seen the append to stream method returning the commit position. The commit position is useful because it tells you the commit position of the last recorded event in the database. And so if you're creating a user interface and you're going to redirect from a form submission to a view, and the view is eventually consistent, you can delay the presenting of that view until the commit position has been processed by a downstream component from which that view will be had. So just to be clear about that, the events are going to be appended, new commit positions are going to be issued, events can be streamed out to a downstream component which is processing the events. It will be recording the commit positions of the events that it's recording. The user interface can then go to the downstream component and wait until the commit position of the events which were created by a command have been processed so that the query does not return a stale view. That's why we are returning commit positions here. So core credentials can be optionally provided to the methods. Sometimes the stream's access control list is altered such that you need to provide other core credentials than the default ones. Alternative core credentials can be constructed with the construct core credentials method. You just pass your alternative username and password in and get a core credentials object, and then you can pass in the core credentials object with the core credentials argument to your method. And user info, user access control, the access control lists can be changed using metadata. The streams have metadata too. So we've seen that events have metadata, streams have metadata too. Stream metadata can be used to alter access control lists as well as other things. You can get the stream metadata using the getStreamMetadata method. It returns a Python dictionary and a integer version number, which is basically the stream position in the metadata stream. The metadata dictionary can be changed. It's just a Python dictionary. You can set values or delete values. And then you can call the setStreamMetadata method to update the stream metadata on the server, passing in the stream name, the metadata itself, and then the current version which you got when you called getStreamMetadata. Internally, these methods use the readStream and append-to-stream methods, so they're kind of like convenience methods, if you like, which hides the details of what a metadata stream is. But if you really want to know, you can just look in the code. Anyway, so that's appending to stream done. And then the next important thing that we really want to do is reading a stream. If we want to reconstruct the state of an aggregate from events that have been recorded, we need to read the stream. We need to get the events for the aggregate from its stream. So we can read a stream by calling the readStream method with a stream name, and then we can iterate over the read response to get the recorded event objects. And so to reconstruct the aggregate from its events, we would probably start with a non-value for an aggregate, and then iterating over the readStream response, we would call mutate aggregate each time we get a new event, and mutate the aggregate with that event, returning the updated value of the aggregate until we've iterated over all the events, and then the aggregate will be in its current state. There are some optional arguments for readStream, such as stream position, backwards, resolve links, and limit. And these can be used to read a stream from a particular position, to read a stream backwards, to return linked events rather than event links, and to limit the number of received events. So we can read streams other than the system streams by using the special EventStoreDB system projection stream names. For example, we can get a list of all the streams by calling readStream with the stream name $streams, and then iterating over them to pull out all the stream names. We can get all of the stream names in a particular category. So say we have this picks off the prefix. So say you've got different streams like order 5, order 6, order 7. If you do like category -order, then you'll get all of the stream names in that category. So the first example here gives you all the streams. The second one gives you all the streams in the category. If we want to get all the events of a particular type in all streams, we can use the event type stream. And if we want to get all the events in a particular stream category, we can use the $CE thing. And for these methods, we need to pass the resolve links equals true. We need to set resolve links equals true because the system projections create streams that have links to the events that you recorded. So to avoid getting the event links, instead to get the linked events, we need to resolve links, and then you'll get your events back. In addition to appending to a stream and reading from a stream, we can delete and tombstone streams. These operations are quite similar but slightly different. When we delete a stream, previously recorded events will not be visible, but more events can still be appended. And if you tombstone a stream, then it's shut, it's closed for business, and you will not be able to append any more events to the stream. In addition to reading from a stream, we can read all the events in the database, and we get a read response, which is very similar to the read response we get when reading from a stream. We can iterate over the events in the read response and do whatever we want with them. The options here are kind of similar, but there's more of them. So firstly, there's a commit position rather than a stream position. The backwards also figures here. We can read backwards. We can also resolve links, and we can limit the number that we get. So if we read backwards with a limit of 1, we'll get the last one, for example. The commit position has to be precisely a commit position that exists in the database. You can't kind of guess the number wrongly and still expect it to kind of find the closest one. It doesn't do that. Also, when we're reading events, there are filter options, which there aren't when you're reading a stream. The filter options implemented on the client are the filter include, filter exclude, and filter by stream name. These are patterns which compile into a single regular expression. The filter include is quite straightforward. It just puts all these things with as alternatives anchored at the beginning and end of the strings which are being matched. The exclude filter does a similar thing, but it uses a slightly more complicated structure to exclude a set of alternatives, but you can look in the code for details. If you want to, it filters by default on the event stream type string. If instead you want to filter on the stream name string, you just need to set filter by stream name as true. So let's move on to catch-up subscriptions. Catch-up subscriptions are very like reading. You get an iterable of recorded events, but the difference is that when the catch-up subscription gets to the last recorded event, it does not stop, but instead blocks. And then it will continue when events are subsequently recorded. So catch-up subscriptions, like reading, catch-up subscriptions can be used to read a stream and to read all events in the database. And the really great thing with catch-up subscriptions is that it can be used to process recorded events with exactly once semantics. So just to detail that a little bit, you just need to use an atomic database transaction to record the position of an event uniquely, along with any new state that results from processing that event, and then use the last recorded position when resuming the subscription. The catch-up subscription will give you every event in the order that it was recorded. The atomic transaction will ensure that the results of processing an event will be recorded at most once. And resuming from the last recorded position will ensure that you receive each event at least once. The combination of these qualities implements exactly once semantics. So let's just look quickly at subscribing to a stream. The subscribe to stream method is like the read stream method. You have to give it a stream name and optionally a stream position. And you iterate over the catch-up subscription just like you iterated over the read response. And then you can read from the end, you can resolve links and so on. You can't read backwards. You just can't do that with the catch-up subscription. They go forwards. And the other thing is to know is that when you're doing a catch-up subscription, you don't get the event at the position that you're asking for, which makes sense if you're going to resume. So the idea is to you start from none, and with a subscription to a stream, you start from none. You'll process your events, recording the stream position, and then when you resume, you will use the last recorded stream position to resume the catch-up subscription, and then you get all of the events. And as we've seen, resolving links is useful when subscribing to system projections. Subscribe to all is very like read all. We can do, and it's very like subscribe to stream, but instead of stream positions, we're dealing with commit positions. We give it a commit position. It should be 0 here. I'm sorry, it's a mistake in the slide. And then we iterate over them, subscribing, resuming from the commit position that we last recorded. The subscribe to all, like read all, has filter options. The filter, actually, I'm sorry, that's not a mistake. The commit position should be none because it starts off. If you give it 0, you won't get the first event. So that's actually not a mistake. I'm sorry. Anyway, so moving on, the read all method had filter options. The subscribe to all method also has filter options. They work in exactly the same way. You can just give them patterns here or just complete strings, and they will be matched precisely, including or excluding according to your choice. And you can, by default, it matches on event types, and you can tell it to match on stream names instead. The next topic is persistent subscriptions, which are a bit like catch-up subscriptions, but the position of your processing is then managed by the server rather than being managed downstream, which is an important difference. The benefit of acknowledging or negatively acknowledging the event back to the server is that it allows you to process the events with groups of consumers. But by recording the position that you've processed upstream and then the new state downstream, you have this thing called dual writing, which can introduce some indeterminacy in your processing. And if you fail to process an event and ask the server to retry, for example, you can get the events out of order. You might get duplicates, and you've got to kind of deal with that in the downstream processing by deduplication, reordering if you need to, and possibly idempotent operations in your downstream event processing, all of which are added complications, but quite common things to do. So we can create there's quite a few methods for persistent subscriptions, whereas the catch-up subscription is just one method, like read that continues. With the persistent subscriptions, we firstly have to create them. Now, like the other methods, we can create a subscription to a stream, or we can create a subscription to all. If we create a persistent subscription to a stream, we have to give it a group name and a stream name. The consumer strategy dispatch to single is the default. I just included it here for illustrative purposes. If we create a persistent subscription to all, we don't give it a stream name, but we can give it filter options. Anyway, so persistent subscriptions, once created, can be read. When we're reading, then we need to provide the same group name and stream name as we passed when we created them. So if we read a subscription to a stream, we need both a group name and a stream name. If we read a subscription to all, we just provide the group name. And like with the read and subscribe methods, we can iterate over the persistent subscription object to get the recorded events. As we can see here, we have a try except block. We'll call a handler, and if there's an exception, then I've got this wrong way around. I'm sorry, I got this wrong way around. If there's an exception, we'll knack first, and then if there isn't an exception, then we'll knack. Just to flip it around in your head. I just made a mistake on the slide. So we'll acknowledge or negatively acknowledge the event according to whether we successfully processed it, and there's actions that we can say when we're knacking according to whether what we want the server to do: retry, park, stop, and so on. When we can, so persistent subscriptions can be updated and also deleted. When we update a subscription to a stream, like when we're reading, we need to pass the same group name and stream name. When we're updating a subscription to all, we just need to provide the group name. We can change the settings of a persistent subscription in this way. There are quite a few settings, and you could look at the documentation to see exactly what you can do. One thing you can't do is change the consumer strategy or the filters, but you can change other things like the message timeout and the max retry count. And then the delete subscription method, there's only one of those. It has an optional stream name. So if you want to delete a persistent subscription to all, you just give it the group name. If you want to delete a subscription to a stream, then you provide the group name and the stream name. In addition to all those methods, there are two more. One is get subscription info, which gives you information on the settings and statistics for a persistent subscription. And you can use the list subscriptions method to get a list of all the subscription info for all persistent subscriptions. There's a lot of details in those subscription info objects. So that brings us to the examples. We have one example, which is getting a little bit up above just recording events and looking at why you would use EventStore. And you would use EventStore if you're doing event sourcing in Python. So let's just look at event sourcing in Python with EventStoreDB. Just for simplicity here, the example will use the Python package event sourcing, which supports event sourcing in Python with a range of persistence modules which encapsulate different event store options, and a domain module which supports a very concise syntax for expressing event sourced domain models. And here we have a dog aggregate class which has two events: the registered event and the trick added event. So we can imagine this dog is part of a database in a dog training school, and firstly the dogs are going to be registered, and then they're going to learn tricks, and the staff at the training school are going to keep a track of which dogs have been registered and which tricks they added. And you can see that the class dog looks very like a normal Python class. It just says class dog. It's got an init thing which takes a name. The name is set, and the name attribute and the tricks attribute is initialized to a list. And when you call the add trick method with a trick, the trick argument is simply appended to the tricks. And the event sourcing library does all of the work of intercepting those method calls, triggering events, collecting the events, and allowing you to record them. The domain model just does the event triggering, and then there's an application module which brings together persistence infrastructure and the domain model. So here we can use it to define application services. For example, register, add trick, and get dog. So the register method takes a name, it constructs a dog, and then saves the dog, which puts the events in the event store. The add trick method, you give it a trick, it gets the registered dog, reconstructing the current state from the recorded events. It adds a new trick to the dog and then saves the dog, appending that new event to the recorded events for that dog. And then the get dog method simply reconstructs the current state of the dog aggregate and returns a dictionary which picks out the attributes of the dog, converting the dog tricks list to a tuple, so that there's no chance of an interface messing up the state of the aggregate. So that's the domain model dog with an application which uses the aggregate and allowing an interface to call into the application. And then to use this with EventStoreDB, all we need to do is install event sourcing EventStoreDB. I think I've spelled that wrong. Package and configure the environment. So the event sourcing EventStoreDB package uses the Python gRPC client for EventStoreDB to make a persistence module which brings it up to a standard interface useful by the application. Then we can construct the training school class, which we can do with any persistence module, but in this case, it's going to be using EventStoreDB. We'll configure the environment variables persistence module so that the application will use the EventStoreDB persistence module. And for that, we need to also set the EventStoreDB URL in the environment. So then after that, we can construct the training school. We can register our dog Buster. We can add a trick rollover, and then we can add another trick fetch ball, and then we can get the dog details from the application with the events stored in EventStoreDB. And this is one we made earlier. So if we look in the event store database, we can see that we have a stream with 3 events: the dog registered, the dog trick added, and another dog trick added, numbered 0, 1, and 2. And if we look at 0, we see that it's got JSON data of the name of the dog Buster. And if we look at event number 1, we see that it has a trick fetch ball. And if we look at event number 2, then we see that it has the trick rollover. And there's various other things we could show about this, but that's all, folks. Thanks very much for coming.
Thank you so much, John. That was awesome. If anyone's got any questions, please let us know. We haven't got a question, John, but we have got a thank you. So Patrick put, John, thank you very much for your effort in bringing event sourcing tools to the Python language. I've learned a lot from your book and repository event sourcing in Python. So that's really, really lovely feedback. Thank you, Patrick.
Thank you, Patrick.
Yeah. Has anyone else got any questions? If you have, then obviously you can send them to me and John if you think of anything afterwards. But in the meantime, thank you so much for that today, John. That was really interesting. Thank you, everyone, for joining us. Bye.